So it only makes sense that following Dr. Alderson, we go right into an IMUs and wearable conversation in the research. So first up, we are going to have Dr. Aguinaldo from Point Loma come back again with Eric Berger, one of the master students there who I actually had the pleasure of working with in a previous job. They will be talking about the validation of wearable sensor and the estimation of elbow valgus torque during baseball pitching. Guys?
Okay. Thanks, Ethan. Just real quickly, I want to introduce you, Eric. Eric was a part of our MSkin cohort about maybe 2-3 years ago, and he has since moved on and actually spent some time with the Tampa Bay Rays. So this particular study he did as part of his master's thesis, it was accepted to be presented at this year's ACSM, but unfortunately due to our current situation, we've kind of had to make adjustments to do a virtual conference. So I'm really excited for him to share. I know that there has been some validation work on the sensor since then, but I'm excited for you guys to learn from Eric what he found in his study. Eric?
Thank you, Dr. Ray. Thank you, Ethan. Good to see you, by the way. My research was done for my master's program about 2 years ago, so keep that in mind. But we did the validation of an IMU sensor in the estimation of elbow valgus torques during the baseball pitch. Obviously, we know that the UCL provides that primary restraint to that valgus stress, and the injury of the UCL has become an epidemic amongst all levels throughout baseball. At the time, the Modus Baseball IMU sensor was in use throughout all levels of baseball without a published independent validation, so we were providing that. For this study, we used 34 healthy male pitchers for the data. Their ages ranged from 13 to 17. We did have more subjects, but at the time, we were forced to cut it short with the deadline for the master's program, so we just kept those 9 subjects that were ranging from ages 18 to 28 out of the data. We used those 34. The subjects were required to be capable of throwing 10 consecutive fastballs at a game-like intensity with no recent injury that could inhibit that effort. We used the Modus Baseball IMU sensor taped over the skin of the UCL, where the UCL is located. And we used a custom wound sleeve that went over that arm and over the reflective markers that were required with the pitch track marker set, while also being recorded by 10 motion capture cameras around that mound. For the data analysis, we found descriptive statistics calculated for both the 3D motion capture system and the Modus Baseball IMU. We also ran Pearson correlations for the concurrent validities through SPSS at a significance level of 0.05. We also ran a degrees of error assessment using the Bland-Altman graph. So for the results, we found the Pearson correlation to be 0.686, and the average of the Modus Baseball recording was 38.3 newtons. The motion analysis was recording at 35.8 newtons. So those were the averages for those two respectively. And the key findings would be that the correlation shows a moderate concurrent validity. And with the data collected and analyzed unto this point of this study, we hypothesized that the device is a valid tool in estimating the elbow valgus torque during the overhand throw. The limitations of this study were that we used 34 pitchers, and their mean age was around 16 years old, give or take 2.9 years. We also used a custom wound sleeve instead of the Modus sleeve that was provided. And there were a couple updates with the iOS that created some difficulties with getting reports back on pitchers and getting that information back instantaneously like you're supposed to. And also the markers were put on the pitchers by different people each time as well. So for conclusions, the future research should focus on using a greater sample size, different levels of play, reliability of all of the metrics, and the other variables as well. So we just looked at arm stress. There's still arm slot, arm speed, shoulder rotation, and multiple other ones. There is also, so for this study, the Modus Baseball IMU would be considered a valid tool in estimating the elbow valgus torque at the pitching elbow. Thank you.
Awesome. Thank you, Eric. Next, we will go to Dan Aucoin from Driveline Baseball. He's going to talk about using paired IMU data for improved player development. Dan?
My name is Dan Aucoin. I'm the co-manager of baseball analytics at Driveline Baseball, also an R&D consultant with the Philadelphia Phillies. Just real quick, disclaimer, all of this data is collected, analyzed, results are processed on the Driveline side of things. So just wanted to say that right off the bat. But with that being said, we can just kind of get into it. Obviously, the motivation and rationale behind this sort of analysis is to gain more insights into KVest, which has become more and more popular. As mentioned earlier in the conference, just the prevalence of wearables are increasing in player development, but the insights may not necessarily make it into the public realm. So basically trying to bridge that gap between what trainers understand, what athletes understand, and what information we have at our disposal to potentially evaluate athletes and get some more quantitatively driven programming is something that I try and tackle. So at Driveline, we collected data from 103 athletes over the past roughly 9 to 10 months, ranging from youth to professional. Swings were taken in a pretty constant environment during a swing design session, what we call a swing design session. So underhand flips only, so batters aren't adjusting for pitch location. They're not having to worry about different pitch types, velocity, all that fun stuff. And really what we try to set out to do at a base level is try and see what correlations exist between the plethora of KVest metrics that get spit out at you and things like bat speed, attack angle, vertical bat angle. And obviously for most people on this call, they know that the signal is pretty low across the board, right? Hitting's an open skill, human movement's complex. And so we wanted to try and build off of that, gain some insights that hopefully can inform our trainers and athletes a little bit better. So we sort of look back to prior research, specifically Ben Hansen's Slugfest talk from 2019, which pretty convincingly made the case that angular rotational velocity, if we're trying to, say, predict bat speed, can be transformed into estimates of rotational kinetic energy throughout the different segments that, say, KVest would provide in a PDF output. And basically we'd be able to get a bit stronger correlation to bat speed if we account for, say, a batter's height and weight. Because obviously a 13-year-old can come to our facility. If they're like 5'8", 120 pounds, they can rotate pretty quickly and get some high numbers on KVest angular rotational velocities, but how that translates to bat speed may not be direct. So we'll talk about that in like a quick minute, but the other thing that we wanted to do was look at KVest PDF export, which provides a range of sort of like ideal bands that athletes are sort of instructed to or suggested to fall in between. So whether it be torso rotation at contact or pelvis forward bend at first move. We wanted to try and see if KVest suggestions sort of link up one-to-one with what we see in the facility, especially as it relates to talent from high school, college athletes, all the way up to affiliate ball. So using trainer intuition and methods, I probably can't dive into too much depth on here, given time constraints. We manipulated KVest bands in one direction or another, weighted some metrics a bit more heavily than others based on their relationship to bat speed, and essentially tried to gain what we call a swing score. So for example, if an athlete is over-rotated with their torso at contact, say at like 110 degrees, that would fall outside of our suggested bands. We'd basically bump them up one flag in their swing score. And so we just add that up at the end of each individual swing for the KVest and blast swings that we've paired together here in the facility. And then each athlete gets an average swing score per, say like per session. And so we were able to give trainers the list of 103 athletes and allow them to rank each athlete on a scale of talent, somewhat arbitrary, 1 to 3, where 1 are our most talented hitters and 3 are our least talented hitters in their opinion. And we can see that overall our most talented hitters get flagged about 3 times per swing, given our underlying criteria, whereas our least talented hitters get flagged about 5 times per swing. And the same sort of relationship holds true between our affiliate ball athletes and our high school level athletes. So a lot of out of sample validation testing needs to be done on these different buckets, these different criterias throughout the swing. But we think it's pretty promising to sort of find this relationship with talent, at least at first, where we can sort of make suggestions to athletes that sort of like suggest that they should fall between certain bands with this given metric on KVest. And so the other thing, of course, is that now that we have this nice relationship between, say, like a swing and talent, other thing is trying to predict bat speed for us. So that's where our estimates of rotational kinetic energy come into play. We can see that once we translate those angular rotational velocities to estimates of rotational kinetic energy by segment, we can see much stronger correlations across the board. And then once this GIF alternates back to the scatter plots I've shown, we can see that on the top, we have our RKEs on the x-axis, bat speed on the y-axis as measured by blast. And we can see it's broken down by segment as well, pelvis, torso, upper arm, hand, from left to right respectively. We can see much stronger relationship across the board relative to angular rotational velocities of the same segment, which are on the bottom row. So that basically, I think, sums up our initial analysis with KVest, where we're at. How we translate that and apply it to the athlete is on this table and visualizations that will shift back and forth here. But essentially, we try and take our swing score, we put it on a plus scale similar to like WRC plus, where like 100 is facility average in terms of the amount of flags per swing that an athlete has at Driveline. If you score a 105, you're 5% above our facility average. If you're a 95, you're 5% below our facility average. And that's just like one way we create a catch-all metric that's sort of simplified for athletes, for trainers, to try and quantify the movement of a player's swing a bit more intuitively for them, so they can just look at one metric and see how they compare to affiliate players versus high school players in terms of the positions they're in throughout the swing as provided by KVest. And then we can standardize our estimates of rotational kinetic energy so that it makes more sense for the athlete. We can see with this particular athlete, they're above facility average in the pelvis, torso, upper arm in terms of rotational kinetic energy, and then fall below facility average when we measure the hands. So potentially a trainer can pick up on that, use that data point, that information source to look at video, talk with the athlete, gain information, and ultimately try and manipulate some programming for them so that they're basically trying to attack their specific deficiencies with a little more specificity than we would be able to otherwise. So that's kind of where we're at. I think KVest can be a pretty powerful tool, especially when paired with Blast. We're just scratching the surface, and this analysis is pretty preliminary, but it's exciting nonetheless. And there's still a lot more that we can be doing. So that's about what I got.
Awesome. Thank you, Dan. So what we are going to do, we'll bring Dr. A and Eric back in here. I see Dr. A. But we'll answer a few questions here that have just been coming. Dr. A, I might send these to you as I don't see Eric.
Yeah, Eric had to cut out. He had to cut out to his job, so I'll take over the Q&A.
All right, so Dr. A, coming to you. So is it evident that there is variability from a mocap lab to mocap lab, and in their own calculations of joint torques? Is there any plan to somehow compare the data to other labs or reproduce this study? An R-squared of 48% seems a little low when looking at IMU sensor as a valid tool when they're trying to have the same measurement.
Agreed. I know there were a few labs that have both MODIS and collected some mocap data. I don't know if Kyle or Joe from Driveline can chime in, but they did a similar study after us, and I believe they found something similar, around 48% shared variance between, at least in the elbow valgus work, between the mocap data and the IMU. Yeah, I agree that it's a little bit strong to say that it's a quote-unquote valid tool, but it is a useful tool to use on the field because it's feasible. And what I've always told coaches, I go, look, if there's some red flags that are being raised with an IMU such as this modus sleeve consistently, then maybe we could send this guy to the bullpen or to the lab and really kind of hone in and dive in a little bit deeper. But at least we kind of get to know where we're at in terms of the quote-unquote agreement or lack of agreement between the IMU and MOCAP. And I agree, the more data we have, the more that we can solidify what that validity is.
Awesome, thank you. Next question is going to you, Dan. So it says, should we use linear regression as opposed to a polynomial regression if we were looking at a relationship in this case? Have you tried linear regression? If so, can you share your findings?
Yeah. So the context maybe helps a little bit. I'll just kind of like talk everything more broadly as far as comparing bat speed to individual KVAS metrics, say at like heel strike, first move, at contact. For sure, nonlinear regression is definitely preferable. You can sort of see that relationship across like multiple variables, maybe with the exception of like peak angular rotation, rotational velocity of the hand. But aside from that, you can clearly, for the most part, see two defined bands where polynomial regression probably is better. And as for sort of predicting bat speed, we just use linear regression off of our estimates of rotational kinetic energy. There's probably a better way to go about doing that, but truthfully, we're looking for more data on that front. The change between using simple linear regression to predict bat speed with angular rotational velocities, our score was like 0.1, and then with estimated rotational kinetic energy was like 0.33. So we're getting there, and there's certainly room for improvement. But yeah, I guess to make a long answer short, the answer is yes.
Okay, awesome. Dr. A, I'll send the next one to you. Any thought to look at pitch style, for example, arm slot, and how it influenced the error in the modus elbow stress measurements?
That's a good question. We did not in this particular analysis. I'd definitely like to look into that because I believe that is one of the metrics that is outputted by the modus, and see how that also agrees to quote-unquote arm slot position, at least the kinematics of the arm slot position as measured with the MOCAP, and see whether or not that's an agreement. But that's something that we could certainly look at because we have the data, and just kind of dive in a little bit more and do that type of a comparative analysis.
Awesome, and we'll finish up with one last one. Dan, coming back to you, asking again if these are linear or non-linear relationships, but it looks like LOESS lines are graphed in the plots, but are the R values from those lines or our standard Pearson linear correlation?
It's just standard Pearson correlation.
Awesome, thank you guys.